Hi, everyone. So this is a brief intermission. In the next video, we discuss how to calculate momentum statistics, averages, standard deviations directly from the wave function. I give you some piece of new information. But I think before that, let's reflect on what that really means. Now, classically, when you think of momentum, you basically think of m times v, right? So classically, P equals mv. So momentum is a measure of velocity. Yes, weighted by the mass, true. You have two particles, one heavier, one lighter. They have equal velocity, but the heavier one has larger momentum. And the reason, let's remember, why do we have this concept momentum? Why can't we just get away with velocity? Because it's the momentum that's conserved. The total momentum of the system that's isolated from the environment is conserved, right? That's not velocity, not the sums of velocities, but the sums of velocities weighted by m. That's why this word exists in the vocabulary. Now, when you look at this, you think v, well, that's just dx dt, or in higher dimensions, you think of velocity vectors, the derivative of the position vector. This is not allowed in quantum mechanics. Why is that not allowed? Because saying things like that is equivalent to to saying that you have a trajectory information. Because if you have a trajectory in one dimension, that would be, for example, just coordinate versus time. If you have a trajectory, you can, if you have a trajectory, then you can calculate, delta x over delta t, take the limit and do whatever you want with it. But this really implies the existence of a trajectory. Trajectories are not allowed in quantum mechanics, and it's formalized by the Heisenberg uncertainty principle. Heisenberg says, well, if you know coordinate, you don't know the velocity, or you don't know the momentum. So you cannot think of trajectories. We already discussed that multiple times. So trajectory viewpoint is inapplicable to quantum mechanics. You see, and therefore you cannot define velocity this way. So what does velocity mean in quantum mechanics? It means nothing but p over m. You can define velocity like that, but it does not mean this. It means this. Like, why would you care to do that? It doesn't contain any more information than momentum does. What does momentum mean in quantum mechanics? Right? We don't want to have a circular argument, right? We don't want to say that momentum equals velocity times m. What does velocity mean? Momentum in quantum mechanics basically means the wave number. Remember this. So momentum tells you about the wave number, i.e. the wavelength. So momentum is really information about the wavelength or a set of wavelengths that make up the wave function. You see, so now this kind of completes the picture. We get away from velocities. We replace that by the statistical picture with wave functions. Well, wave functions are waves. Waves have frequencies, that they have wave numbers. Momentum is really a measure of the wave number of your wave function, or equivalent to the wavelength, because remember k equals 2 pi over the wavelength. The point is, momentum, it encodes in it the wavelength of the wave function. Or the wave function is made up of multiple harmonics, then you would have a spread of wave numbers, which is equivalent to having different possible outcomes for momentum when you do measure it. But the point is, measuring momentum is equivalent to measuring wavelength. Momentum, wavelength, momentum, wavelength, momentum, wavelength. And with that definition, feel free to divide by m. It's not against the law. You can define velocity like that, but it does not mean this. So maybe a week ago, a couple weeks ago, you had a homework exercise where you're given the plane wave function and you were asked to calculate energies, kinetic energy. And some people probably said something like 1/2 mv squared, where the way they got the v is they divided a wavelength by the period, right? So something like that. Or they multiplied, they got the k, they got the omega. From that, they got the wavelength and the period, and they divide by wavelength by the period. When you do that, you're actually doing that. So when you were given the wave function, that's something like a e to the I kx minus omega t, right? And you could say v equals a wavelength over the period, which is the same as omega over k. What you're really doing is this is, you see, this is distance and this is time. Not allowed. So what is this velocity anyway? It is some kind of a velocity. It's the velocity of the wave function. When I showed you simulations of wave functions diffracting through slits, it's clearly some kind of a wave packet. It moves. The motion of the wave is deterministic. But it's the motion of the wave. It's the motion of the probability wave. It's not the motion of the particle. The wave moves like a classical wave, but the particle doesn't. You use that wave to get statistics of particle locations, particle momentum, whatever. So this is the velocity. This is the velocity of the wave function. It's not the same as the velocity of the particle. And again, the only sense in which you can talk about velocity in quantum mechanics is like this. But it does not mean dx dt, delta x over t, distance over time. So the right quantity in quantum mechanics is momentum, which is really a measure of wave number or wavelength. And if you know momentum, you can calculate energies and things like that. So it's a useful quantity to know. And the next video discusses how to obtain statistics of momentum directly from the wave function. All right? Okay.